A glass rests on the table. It appears solid, stable, dependable. If a hand reaches toward it, the expectation is simple. Contact will occur. Pressure will be felt. The world will behave exactly as it always has. This confidence feels so obvious that it rarely receives any thought at all. Solidity seems like the most basic property reality can possess. A surface is either there or it is not. Weight is either supported or it is not. The entire structure of daily life rests quietly on this assumption. Yet beneath that certainty, something deeply unsettling is happening. At the scale of atoms, there is no solid contact taking place at all. The atoms that form the glass and the atoms that form the hand never actually meet. Both are surrounded by clouds of negatively charged electrons that repel each other long before any physical collision could occur. What feels like touch is the resistance of invisible fields pushing against one another across empty space. The sensation of pressure is not matter pressing into matter. It is force preventing overlap. If the empty space inside atoms were removed, the entire human population could theoretically fit into a volume smaller than a sugar cube. Almost everything that appears dense and continuous is in fact structured emptiness, held together by forces that cannot be seen. The surface of the table is not a barrier made of solid material. It is a boundary created by interactions between electric charges. The stability of the world is not built from contact. It is built from exclusion. Vision seems like a more trustworthy guide. Light reflects from objects, enters the eye, and produces the experience of shape and color. This process feels immediate, almost instantaneous, as though reality is being streamed live without delay. But the biological pathway between the eye and the brain introduces a measurable lag. Photons strike the retina, electrical signals travel through neural tissue, and the brain assembles a three-dimensional model of the scene. Even under ideal conditions, the experience of sight is already tens of milliseconds behind the physical event that caused it. This delay means that what appears to be the present is actually a reconstruction of the recent past. The world being experienced is not the world as it exists in this exact moment. It is a prediction corrected by incoming data. The brain continuously edits the timeline, smoothing over gaps so that motion appears fluid and synchronized. Without that internal editing, reality would feel fragmented and disjointed. The seamless flow of experience is not raw input. It is an active reconstruction. The unsettling implication is that the most trusted senses do not deliver reality directly. They provide a model designed to be useful. Evolution did not shape perception to reveal the deepest structure of the universe. It shaped perception to guide survival. A nervous system that simplifies complexity into manageable symbols has an advantage over one attempting to process every microscopic detail. The environment becomes a set of actionable signals rather than an overwhelming flood of data. This means the objects that appear stable and familiar may function more like interface icons than faithful representations. The colors, textures, and boundaries that define the visible world could be efficient shortcuts rather than literal descriptions. Just as a computer desktop displays simple shapes to represent vast amounts of hidden code, perception may present an accessible surface that conceals the underlying machinery. If this is true, the immediate environment is not being experienced as it truly exists. It is being rendered as something easier to navigate. The solid world becomes a translation layer between biological limitations and an underlying structure that is far stranger than intuition suggests. The table is not truly solid. The present moment is not truly immediate. The senses are not revealing the full signal. Once that possibility is accepted, a more difficult question emerges. If the most basic features of everyday experience are approximations, What happens when investigation continues beyond the limits of perception and deeper into the structure of matter itself? Beyond the limits of ordinary perception, the search for solidity becomes an investigation into structure. The first layer beneath everyday experience is the atom, once imagined as a tiny, indivisible sphere. Early models pictured it as a miniature solar system, a dense nucleus surrounded by orbiting electrons. This image was comforting because it preserved the idea that matter was still made of small but definite objects. Yet even this familiar picture does not survive careful measurement. Electrons do not move along neat circular paths. They exist as probability distributions, regions where a particle might be found rather than places where it definitively is. Inside the atom, the nucleus appears at first to restore the sense of substance. Protons and neutrons cluster tightly together, carrying nearly all the mass. But when instruments probe deeper, these particles also dissolve into something less tangible. They're composed of quarks bound together by gluons, excitations of underlying quantum fields that permeate all space. A quark is not a miniature marble hidden inside matter. It has no measurable size and no clear boundary. It is better described as a point where a field has taken on a specific value. The deeper the investigation goes, the less the universe resembles a collection of objects, and the more it resembles a network of relationships expressed mathematically. At this level, matter behaves in ways that resist common sense. Instead of existing as definite pieces located in precise positions, particles occupy a haze of potential outcomes. The language of physics shifts from nouns to probabilities. An electron is not simply somewhere. It has a likelihood of being detected in many possible places, until an interaction forces a single outcome. The solidity that defined the glass on the table becomes an emergent effect of countless interactions, rather than a property embedded in any individual component. This transition from certainty to probability becomes impossible to ignore when examining one of the most famous experiments in scientific history, the double-slit. In its simplest form, particles such as electrons are fired toward a barrier with two narrow openings. If these electrons behave like tiny pellets, each one would pass through one slit or the other, producing two clear impact bands on the detection screen behind. Instead, when no attempt is made to observe which path the electron takes, the screen fills with an interference pattern. The pattern resembles the ripples formed when waves pass through two openings and overlap, creating alternating bands of reinforcement and cancellation. The disturbing implication is that each electron behaves as if it travels through both slits simultaneously, interfering with itself before landing as a single localized detection. The particle is not choosing a path in the classical sense. It exists as a spread-out wave of probability until the moment it is measured. When detectors are placed at the slits to determine which route the electron actually takes, the interference pattern disappears. The electrons begin behaving like discrete impacts, forming two bands exactly as expected for solid objects. The mere act of acquiring path information alters the outcome. This shift in behavior is not caused by clumsy equipment disturbing the particle in some crude mechanical way. Even extremely delicate measurement techniques that minimize physical interaction still collapse the wave pattern. The decisive factor is the availability of information about the system. When which path data exists, even in principle, the interference vanishes. When that information is erased or never recorded, the wave behavior returns. The experiment suggests that the universe does not commit to a single definite history until the conditions for observation demand it. The implications of this result divided the founders of modern physics. Albert Einstein argued that the electron must possess a definite path, regardless of whether it was measured. From this perspective, quantum mechanics was incomplete. missing hidden variables that preserved an objective reality beneath the statistical predictions. Nature, in this view, followed a precise script even if it remained temporarily concealed. Niels Bohr countered that the demand for a definite path was itself a classical prejudice. According to the emerging quantum framework, properties such as position do not exist in a determinate form until an interaction forces them into one. For decades, this disagreement remained philosophical because no experiment could directly distinguish between the two positions. That changed when John Bell derived a mathematical inequality describing the maximum level of correlation that hidden variables could produce between separated particles. If Einstein's picture of local realism were correct, entangled particles could only coordinate their outcomes up to a strict statistical limit. Any stronger correlation would imply that the particles were not carrying pre-written instructions. Subsequent experiments tested Bell's prediction with increasing precision. Pairs of entangled photons were generated and sent to detectors separated by large distances. Measurement settings were changed rapidly to prevent any exchange of signals between the particles at or below the speed of light. The results repeatedly violated Bell's limit. The correlations between the particles were stronger than any local hidden script could explain. The data indicated that the properties measured were not predetermined. Instead, they appeared to crystallize into definite values only at the moment of observation. These findings forced physicists to abandon at least one deeply held assumption about the structure of reality. Either influences can propagate faster than light, or objects do not possess independent properties prior to measurement. Most interpretations retain the cosmic speed limit, and instead accept that realism, the idea of pre-existing definite attributes, does not hold at the quantum level. Entangled particles behave as components of a single extended system even when separated by vast distances. The universe, at its smallest scales, refuses to be divided cleanly into isolated pieces. Further experiments complicated the picture even more by challenging the direction of cause and effect. In delayed choice setups, the decision about how to measure a particle is made after it has already passed through the apparatus. Under classical reasoning, the earlier behavior should be fixed and unaffected by later choices. Yet the statistical outcomes align with whichever measurement configuration is ultimately implemented. The particle's past behavior appears consistent with information that becomes available only afterward. The history recorded is not independent of the measurement context. These results do not imply that time is literally being rewritten in a dramatic cinematic sense. Instead, they reveal that quantum events cannot be described as having a single classical trajectory independent of the full experimental arrangement. The concept of a fixed path existing prior to measurement loses meaning. Reality at this scale is better represented as a set of correlated possibilities that resolve only when an interaction produces a record. When these ideas are extended to more complex scenarios, the notion of observer-dependent facts becomes difficult to avoid. Consider a sealed laboratory in which an experiment is performed and a definite result is recorded inside. From the perspective of the scientist within the lab, the outcome is established. From the perspective of an external observer who has not interacted with the system, the combined laboratory can still be described as a superposition of possible states. Both descriptions are internally consistent within their respective frameworks. The tension arises because classical intuition expects a single universal account that all observers must share at every moment. Modern interpretations attempt to reconcile this by treating measurement as an interaction that updates the information available to each observer rather than revealing a pre-written outcome. The wave function, in this view, encodes expectations about future observations, rather than a literal physical wave spread through space. When a measurement occurs, the update reflects a change in knowledge about the system. Different observers may legitimately assign different descriptions, until their information is brought into alignment through communication. Underlying these conceptual debates is a growing recognition that information may be more fundamental than matter itself. John Wheeler proposed that every physical quantity can ultimately be traced back to binary distinctions, yes or no questions resolved through interaction. In this framework, the tangible features of the universe emerge from countless acts of information exchange. The solid table, the measurable position of an electron, and the recorded outcome of an experiment all represent stabilized answers within a network of possibilities. Seen through this lens, the strange efficiency of quantum behavior begins to resemble a system that defers unnecessary detail. Instead of calculating and storing a definite state for every component at every moment, the underlying process maintains a spectrum of potential outcomes. Specific values are produced only when an interaction demands them. This approach conserves informational resources while still allowing consistent large-scale structure to emerge from repeated measurements. The familiar world is then the accumulated record of countless resolved questions, layered into the stable patterns that define everyday experience. As investigation continues beyond the scale of individual particles, the consequences of an information-first description become increasingly difficult to dismiss as mere abstraction. Quantum systems do not simply behave probabilistically in isolation. They form relationships that bind distant components into unified states. Entanglement is not a rare anomaly but a routine feature of interactions. When two particles are produced together in a single quantum process, their properties can become linked in such a way that neither possesses an independent description. The combined system has a well-defined set of correlations, yet each part on its own remains indeterminate until measured. This relationship persists regardless of distance. Experiments have separated entangled photons by many kilometers, even between ground stations and orbiting satellites, and the correlations remain intact. When one particle is measured and yields a particular outcome, the partner immediately displays the complementary result predicted by the shared state. No usable signal travels between them faster than light, yet the joint description behaves as a single entity distributed across space. The classical picture of the universe as a collection of independent objects exchanging local influences begins to fracture under this evidence. Separation does not always imply independence. The unsettling feature is not merely that distant events are correlated. It is that the correlated values do not exist prior to measurement. The outcomes are not revealed like hidden cards in sealed envelopes. They are generated at the moment of interaction in a way that preserves the statistical rules of the shared state. The measurement does not uncover a pre-written answer stored inside the particle. It participates in producing the answer that becomes part of the physical record. Reality at this level resembles a negotiation between possibilities constrained by mathematical structure, rather than a retrieval of fixed properties. When extended across many components, entanglement forms vast networks of correlation that encode how systems relate to one another. Increasingly, theoretical work suggests that these correlations may do more than link particles. They may help generate the geometry of space itself. The proposal known as emergent spacetime treats distance not as a fundamental ingredient, but as a measure of how strongly regions of the universe are connected through quantum information. Highly entangled regions appear close because their states are tightly interwoven. Weakly connected regions appear distant because their correlations are sparse. One provocative formulation of this idea is summarized by the relation often written as ER equals EPR. The expression links Einstein-Rosen bridges, commonly called wormholes, with Einstein-Podolsky-Rosen correlations, the formal description of entanglement. In simplified terms, it suggests that the mathematical structure connecting entangled systems is equivalent to a geometric bridge within spacetime. These bridges are not traversable tunnels large enough for matter to pass through, yet they provide a conceptual link between information theory and gravitational geometry. Space begins to resemble a fabric woven from countless microscopic threads of correlation. If geometry is an emergent property of information, then the familiar sense of depth and extension may not be fundamental features of reality. Evidence from black hole physics reinforces this possibility. When matter collapses into a black hole, classical reasoning predicts that information about the infilling material should be lost behind the event horizon. Quantum mechanics forbids such destruction. The conflict between these principles produced the information paradox, a crisis that forced a re-evaluation of how information is stored in extreme gravitational environments. Calculations showed that black holes emit a faint thermal radiation due to quantum effects near the horizon. Over immense spans of time, this Hawking radiation allows the black hole to evaporate. If the radiation carried no detailed information about what fell inside, then the total information content of the universe would decrease, violating quantum unitarity. Resolving this contradiction led to the proposal that the information describing infailing matter is not destroyed within the volume of the black hole, but encoded on its surface. The event horizon behaves like a storage boundary whose area determines the maximum information content. This insight evolved into the holographic principle. The maximum entropy, or information capacity, of any region scales with the surface area that encloses it rather than its volume. A three-dimensional region can be fully described by data residing on a two-dimensional boundary. In ordinary experience, a label on the outside of a container merely summarizes what lies within. In the holographic framework, the boundary description is not a summary, but a complete encoding. The interior becomes a projection generated by information distributed across the enclosing surface. Mathematical development strengthened this perspective. When dualities were discovered linking gravitational theories in higher dimensional spaces with quantum field theories defined on lower dimensional boundaries, the correspondence demonstrated the two radically different descriptions, one containing gravity within a curved volume and another lacking gravity on a flat boundary, could produce identical physical predictions. Events that appear to unfold within depth can be equivalently described as interactions occurring on a lower dimensional surface. The experience of volume becomes a derived effect rather than a primary ingredient. If the universe operates under similar principles, the sense of inhabiting an extended three-dimensional arena may arise from informational processes encoded elsewhere. The analogy to a projected image is imperfect, but suggestive. A cinematic scene appears to contain distance and motion, yet the underlying data resides on a flat medium. The depth is reconstructed by interpretation of encoded signals. In a cosmological context, the boundary that carries the full description could be the horizon defined by the observable limits of spacetime. Attempts to probe the smallest scales of geometry introduce another constraint on the classical picture. Quantum gravity arguments indicate that there exists a fundamental limit to how finely space can be divided. The Planck length sets a scale below which the concept of distance loses operational meaning. Measurements attempting to resolve intervals smaller than this threshold would require energies so large that the region would collapse into a microscopic black hole, preventing further localization. The continuum assumed by classical physics gives way to a discrete structure with finite resolution. A discrete foundation implies that smooth motion is an emergent approximation. Trajectories that appear continuous at human scales may correspond to transitions between adjacent quantum states, separated by intervals too small to detect directly. Just as a high-resolution display produces the illusion of fluid movement through rapid updates of individual pixels, spacetime may present a seamless facade built from finite informational units. The apparent continuity of geometry becomes a coarse-grained description of underlying discreteness. Within this informational framework, Gravity itself may arise from statistical behavior of microscopic degrees of freedom, rather than existing as a fundamental force in its own right. Some approaches describe gravitational attraction as an emergent tendency for systems to evolve toward configurations that maximize entropy under constraints imposed by information content. Massive objects influence the distribution of underlying states, and the resulting gradients manifest as curvature of spacetime in the effective description. The familiar pull that binds planets to stars may reflect deeper bookkeeping of information rather than a primitive interaction. If information is the substrate from which geometry and matter emerge, then the flow of time must also be reconsidered. At the level of fundamental equations describing quantum fields and relativistic motion, there is no preferred direction distinguishing past from future. The mathematical relations remain valid if time is reversed. The asymmetry experienced in everyday life arises from thermodynamic considerations. Entropy, a measure related to the number of microscopic configurations consistent with a macroscopic state, tends to increase in closed systems because there are vastly more disordered arrangements than ordered ones. The early universe appears to have begun in an extremely low entropy condition, a highly ordered configuration that allowed gradients of energy to exist. As the cosmos evolves, those gradients dissipate. Stars convert concentrated nuclear fuel into diffuse radiation. Complex structures form locally while exporting greater disorder to their surroundings. The sensation of time flowing forward corresponds to the progression from rare ordered states toward overwhelmingly probable disordered states. Memory records past configurations because they leave imprints that persist as entropy increases. This thermodynamic arrow carries long-term consequences. If expansion continues and energy becomes evenly distributed, the universe approaches a state in which no significant gradients remain to drive physical processes. Stars exhaust their fuel, stellar remnants cool, and even black holes gradually evaporate through quantum emission. The end state, often termed heat death, is not an explosive finale, but a uniform equilibrium in which no macroscopic change occurs. With no differences in temperature or density, no work can be extracted and no new structure can form. Time loses practical meaning because successive moments become indistinguishable. Information processing itself is subject to thermodynamic cost. Landau's principle establishes that erasing a single bit of information necessarily releases a minimum amount of heat into the environment. Computation can be performed reversibly in theory, but any operation that resets memory incurs an energetic penalty. If the universe functions as a vast information processor, every irreversible interaction contributes to the overall increase in entropy. The accumulation of waste heat is not merely a byproduct of human technology, but a fundamental constraint linking knowledge, memory, and thermodynamics. Alternative cosmic risks arise from the structure of quantum fields that define the vacuum state. The vacuum is not empty in an absolute sense, but represents the lowest energy configuration available to the fields. Current measurements suggest that the present vacuum may be metastable, residing in a local minimum rather than the deepest possible state. Quantum tunneling could, in principle, trigger a transition to a lower energy configuration. Such a transition would propagate as an expanding bubble, altering the values of fundamental constants within it. Chemistry and stable matter might not survive inside the new phase. The probability and timescale for such a transition remain highly uncertain, and the scenario may never occur within the lifetime of the observable universe. Nonetheless, its possibility illustrates that even the baseline properties of reality are contingent on the structure of underlying fields. The constants that permit atoms, stars, and biological systems are not guaranteed to persist indefinitely. The stability of the environment that supports complex organization depends on parameters set by quantum conditions that could, in principle, shift. In extremely long-lived universes, statistical fluctuations introduce another conceptual challenge. Given enough time, random rearrangements of particles could produce localized pockets of order even in a near equilibrium background. The spontaneous assembly of a minimal self-aware structure would require far fewer coordinated degrees of freedom than the recreation of an entire cosmological history. This observation leads to the hypothetical scenario of isolated observers emerging briefly from thermal noise with internally consistent but fictitious memories. The argument does not assert that such entities exist in practice, but highlights tensions between certain cosmological models and assumptions about typical observers. These considerations reinforce the central theme that information, probability, and correlation govern the deepest levels of description. Matter, geometry, and temporal flow appear as stable patterns arising from underlying statistical processes. The world experienced at human scale remains reliable because immense numbers of interactions average out microscopic uncertainty into consistent macroscopic behavior. Tables support weight, planets follow predictable orbits, and biological systems maintain coherence across vast ensembles of particles. The classical world is not an illusion in the sense of being false. It is an effective layer that emerges from a substrate whose rules differ profoundly from everyday intuition. As theoretical frameworks continue to develop, the boundary between observer and observed becomes less sharply defined. Measurement is not an external act performed on a passive system, but an interaction between components of a larger network. Each recorded outcome contributes to the shared informational structure that constitutes the physical record of the universe. Reality, in this view, is the accumulation of consistent correlations maintained across countless exchanges of energy and information, stabilized into the patterns that persist long enough to be recognized as objects, histories, and laws. Within this evolving picture, the role of observation becomes less about conscious awareness in the everyday sense and more about interaction that leaves a durable record. Any process that entangles a system with its surroundings effectively selects one outcome from a range of possibilities and distributes the information into the environment. This spreading of information, often described as decoherence, explains why quantum behavior becomes difficult to observe at larger scales. The delicate superpositions that exist in isolated systems are rapidly converted into stable classical outcomes when countless surrounding particles record correlated states. A grain of dust floating in a beam of light is continuously struck by photons, air molecules, and thermal radiation. Each interaction leaks information about its position into the environment. The combined effect is that any coherent quantum ambiguity is effectively erased almost instantly. The dust grain behaves as though it possesses a definite trajectory, because the surrounding world has already registered and reinforced that trajectory through countless microscopic exchanges. Classical certainty emerges not because quantum rules stop applying, but because the information about one outcome becomes overwhelmingly distributed. This perspective reframes measurement as a physical process embedded within the same laws governing everything else. The collapse of a probability distribution does not require a special intervention from outside nature. It occurs when a system becomes so strongly correlated with its environment that alternative outcomes can no longer interfere. The record of the event is copied into many degrees of freedom, stabilizing a single branch of history that persists into the future. The familiar solidity of everyday objects is therefore a consequence of continuous information sharing across enormous networks of interacting particles. Even with this clarification, the question remains of how different observers reconcile their accounts. When two observers later compare notes, their records must agree for the world to appear consistent. The exchange of information between them entangles their respective memory states, aligning their descriptions. Prior to that interaction, each may legitimately assign a different probability distribution based on available data. After communication, the combined system contains a shared record that becomes part of the stable classical narrative. Agreement is not assumed from the start. It is achieved through physical interaction that synchronizes information. This emphasis on information exchange extends naturally to the structure of spacetime itself. If geometry arises from patterns of correlation, then large-scale connectivity reflects the cumulative history of interactions. Regions that have exchanged vast amounts of information become tightly linked within the emergent fabric, while regions with little shared history appear distant or causally disconnected. Cosmological horizons mark boundaries beyond which correlations have not yet formed within the lifetime of the universe. Distance becomes a statement about relational structure rather than an absolute container. Black holes provide an extreme testing ground for these ideas because they concentrate enormous entropy within a compact boundary. When matter approaches the event horizon, its detailed state becomes scrambled into the degrees of freedom associated with the surface. From an external viewpoint, the information is not lost, but transformed into a highly complex pattern distributed across the horizon. As Hawking radiation is emitted, subtle correlations within that radiation are believed to carry the encoded information back into the wider universe over immense timescales. The process is not practically reversible, yet in principle, the total informational content remains conserved. The recognition that surface area governs information capacity leads to surprising constraints on how much structure can exist within any region. Attempts to pack more entropy into a volume eventually produce gravitational collapse, forming a new horizon that limits further storage. The universe enforces a maximum density of distinguishable states. This bound suggests that reality has a finite number of degrees of freedom within any finite region, reinforcing the notion that the physical world operates with a limited informational budget. Infinite precision is replaced by discrete possibilities that can be counted. Within such limits, complexity emerges through organization rather than unlimited resources. Stars form when gravitational attraction concentrates diffuse gas into dense cores where nuclear fusion ignites. Galaxies assemble as countless stellar systems orbit within shared potential wells. Biological systems arise when chemical networks harness energy gradients to maintain ordered structures far from equilibrium. At each scale, local decreases in entropy are balanced by larger increases elsewhere, consistent with the overall thermodynamic direction. The persistence of intricate patterns depends on continuous throughput of energy and information. Life exemplifies this dynamic balance. A living cell maintains internal order by importing low-entropy nutrients and exporting waste heat and degraded molecules. The genome stores instructions that guide the synthesis of proteins, yet the fidelity of replication is never perfect. Mutations introduce variation, and selection preserves configurations that remain stable under environmental pressures. Over vast spans of time, these incremental changes generate organisms capable of sensing, predicting, and acting upon their surroundings. Cognition becomes an extension of the same informational processes that govern simpler chemical networks. Neural systems, in particular, demonstrate how integrated information supports coherent behavior. Billions of interconnected neurons exchange electrical and chemical signals, forming dynamic patterns that encode memory and expectation. When sensory input arrives, it is compared against internal models built from past experience. Predictions are updated, and actions are selected that tend to reduce uncertainty or maintain stability. Conscious awareness, whatever its precise mechanism, accompanies highly integrated states in which many subsystems contribute to a unified representation. The brain functions as a continuously adapting inference engine embedded within the physical world it seeks to understand. Some theoretical approaches attempt to quantify this integration by measuring how strongly the components of a system constrain one another's possible states. A network in which every part influences many others possesses high integrated information, while a collection of independent elements possesses little. Under this view, experience corresponds to the degree of unified causal structure present within the system. The concept remains under active debate, yet it illustrates how informational organization can be treated as a physical property subject to analysis, rather than a purely abstract notion. Speculative models have explored whether quantum effects might play a functional role in biological processes beyond known examples such as photosynthetic energy transfer or magnetodeception in certain species. Proposals involving microscopic structures within neurons suggest mechanisms by which coherent states could persist long enough to influence neural computation. Experimental evidence for sustained quantum coherence in the warm, noisy environment of the brain remains limited, and many researchers remain skeptical. Nonetheless, the broader point stands that biology can exploit subtle physical phenomena, when doing so provides an advantage in efficiency or sensitivity. Regardless of the precise details of consciousness, the act of observation in physics does not require human awareness specifically. Any interaction that produces a stable correlation counts as a measurement. A photon scattering from a surface and leaving a trace in the environment is sufficient to select an outcome. Human perception is simply one layer in a hierarchy of information processing systems that extend from fundamental particles through complex organisms. The universe records its own state continuously through the web of interactions that bind its components. This perspective softens the apparent divide between subject and object. Observers are themselves physical systems, participating in the same informational exchange as everything else. Knowledge is not extracted from a passive world, but constructed through engagement with it. Each measurement updates both the system being measured and the apparatus performing the measurement. The resulting record becomes part of the shared structure that constrains future possibilities. Reality is not a static inventory of properties, but an evolving network of correlations stabilized over time. The flow of time, when viewed through this informational lens, corresponds to the accumulation of records that cannot be fully undone. Every irreversible interaction leaves traces dispersed across many degrees of freedom. These traces define the difference between past and future, by making certain configurations vastly more probable in one temporal direction. Memory itself is a physical imprint stored in stable patterns of matter. The asymmetry between remembering and predicting reflects the direction in which entropy increases and records accumulate. On cosmological scales, the expansion of space influences how information spreads. As regions move beyond each other's horizons, their ability to exchange signals diminishes. Correlations established early in the universe become stretched across vast distances, visible today as subtle patterns in the cosmic microwave background. The large-scale structure of galaxies traces the amplification of tiny primordial fluctuations. Information seeded in the initial conditions propagates forward, shaping the distribution of matter across billions of light-years. Even as entropy increases globally, pockets of complexity persist wherever energy gradients remain. Around stars, planetary systems maintain conditions that allow chemistry to operate far from equilibrium. Within such environments, cycles of energy flow support ecosystems that continually process information about their surroundings. The persistence of these ordered islands depends on the continued availability of usable energy. As stellar populations age and gradients diminish, the capacity for sustained complexity gradually declines. Long-term projections suggest that after the era of active star formation ends, the universe will be dominated by remnants such as white dwarfs, neutron stars, and black holes. Over timescales vastly exceeding the current age of the cosmos, gravitational interactions will scatter these objects, and black holes will slowly radiate away their mass. The informational content, once concentrated in luminous structures, will be dispersed into increasingly diffuse radiation. The approach toward equilibrium continues, though at a pace that renders the process effectively static on any human timescale. Against this backdrop, the present epoch represents a transient window in which gradients remain strong enough to support rich structure. The existence of observers capable of reflecting on these conditions depends on the same thermodynamic flow that will eventually erase the distinctions they rely upon. Awareness arises within a system that is simultaneously generating and dissipating the order required for its own operation. The capacity to model the universe is itself a product of the processes that ensure the universe will not remain forever in its current state. Yet despite the underlying uncertainty and eventual decline, the reliability of physical law within accessible domains remains extraordinary. Predictions based on quantum electrodynamics match experimental results to many decimal places. Gravitational dynamics guides spacecraft across interplanetary distances with remarkable precision. The stability of these frameworks indicates that, while the foundational description of reality may be probabilistic and information-driven, the emergent regularities at larger scales provide a consistent stage on which complex phenomena can unfold. Understanding reality as an evolving informational structure does not render everyday experience meaningless. Instead, it situates familiar objects and events within a broader hierarchy of description. The glass on the table remains dependable because the collected behavior of its constituent particles has settled into a stable configuration reinforced by constant interaction with the environment. The predictive success of classical models at macroscopic scales reflects the averaging of vast numbers of microscopic degrees of freedom into smooth, repeatable patterns. As inquiry continues, new experiments probe regimes where gravitational and quantum effects intersect, seeking a unified account that preserves both informational conservation and geometric consistency. Advances in quantum computing, precision measurement, and astronomical observation provide increasingly sensitive tests of foundational principles. Each refined measurement extends the network of correlations that constitutes the empirical record, narrowing the range of viable theories. The pursuit does not eliminate uncertainty entirely, but progressively reshapes the probability landscape within which future discoveries will emerge. As the investigation reaches its furthest horizon, the accumulated evidence forms a picture that is both unsettling and strangely coherent. The world that appears solid is revealed as structured emptiness, stabilized by forces. The objects that seem permanent are patterns sustained by continuous exchange of energy and information. The events that feel immediate are reconstructions assembled from delayed signals. None of these insights invalidate the reliability of experience at human scale, yet together they suggest that everyday reality is an effective layer resting on deeper processes that do not resemble common intuition. The transition from matter to information reframes the oldest question about what the universe is made of. Early models relied on tangible substances that could be imagined as tiny fragments of the whole. Modern physics replaces those fragments with states, correlations, and constraints that can be expressed precisely in mathematics but resist visualization. A particle becomes an excitation of a field. A field becomes a carrier of possible values distributed across space. Space itself becomes an emergent structure reflecting patterns of entanglement. Each step removes another familiar anchor while preserving predictive power. This shift does not eliminate objectivity. Instead, it relocates it. The consistent features of the universe are encoded in the rules governing how information can be created, transformed, and shared. Conservation laws express limits on how states evolve. Symmetries constrain which transformations leave physical predictions unchanged. Probability amplitudes determine how likely different outcomes are when interactions occur. These elements provide a stable framework that remains valid regardless of which specific events are realized within it. Within that framework, observation is understood as participation in the unfolding network of correlations. Measuring devices, biological sensors, and environmental interactions all contribute to the stabilization of outcomes. The resulting records accumulate into a shared history that can be consulted, compared, and extended. The apparent solidity of the past reflects the redundancy of these records across many degrees of freedom. Once information about an event has been widely distributed, reversing it would require coordinating an astronomical number of components, rendering practical reversal effectively impossible. The recognition that information has physical cost adds a further constraint on how the universe evolves. Every irreversible operation increases entropy by dispersing previously localized distinctions into broader environments. Memory formation, computation, and radiation all contribute to this gradual dilution. The arrow of time aligns with the direction in which distinguishable states become harder to reconstruct. Order can still arise locally where gradients exist, but the global trend favors equilibrium. The present era of active structure is therefore contingent on conditions established early in cosmic history. Despite this long-term drift, the universe exhibits remarkable efficiency in how it allocates its informational resources. Quantum systems maintain superpositions where detail is unnecessary, resolving specific values only when interactions demand them. Gravitational bounds limit the density of distinguishable states within any region, preventing runaway accumulation that would violate consistency. Biological systems encode vast complexity in compact genetic sequences and exploit environmental energy to maintain coherence. Across scales, stable patterns persist by balancing the costs of information storage against the benefits of organization. The possibility that geometry itself is derived from correlation further unifies these observations. Distance, curvature, and connectivity can be interpreted as macroscopic reflections of microscopic relationships. Regions that share dense networks of entanglement behave as contiguous, while weakly linked regions appear remote. Horizons mark limits beyond which correlations have not yet formed within the observable record. In this view, the stage on which physical processes unfold is continuously generated by the same informational exchanges that those processes enact. Black holes remain the most extreme demonstration of these principles. Their horizons encode the maximum entropy permitted for a given boundary, converting infailing detail into highly scrambled surface data. Hawking radiation gradually releases that information back into the wider universe in a form that preserves overall consistency while erasing practical recoverability. The paradox that once threatened the foundations of theory now serves as a guidepost, indicating that any complete description must treat information as indestructible even when its original organization is lost. At cosmological scales, the same informational accounting governs the evolution from early uniformity to present complexity. Tiny primordial fluctuations were amplified through gravitational instability, seeding the distribution of galaxies. Nuclear processes within stars generated the heavier elements required for chemistry and life. Each stage depended on the availability of gradients that allowed energy to flow and structure to emerge. The resulting hierarchy of organization, from subatomic fields to biological cognition, represents successive layers built upon the preservation and transformation of information. The eventual fading of those gradients does not negate the significance of the structures that arise while they persist. Predictive laws remain valid within the domains where they have been tested, enabling reliable navigation of both natural and technological environments. The capacity to measure, model, and communicate findings extends the shared informational record, reducing uncertainty about many aspects of the world even as deeper questions remain open. Scientific progress functions as a cumulative refinement of correlations between theory and observation. Speculative scenarios such as vacuum, instability, or extremely long-term statistical fluctuations highlight the contingent nature of current conditions without providing evidence that such outcomes are imminent. They serve primarily to delineate the boundaries of what existing theories permit. The practical reality within accessible timescales is one of stable constants, repeatable interactions, and gradual thermodynamic change. The distinction between conceivable possibilities and empirically supported expectations remains central to responsible interpretation of foundational physics. Within the informational perspective, the presence of observers is not an external anomaly, but a natural consequence of systems capable of maintaining and updating internal models. Organisms that track regularities in their environment gain survival advantages, leading to the evolution of increasingly sophisticated representational capacities. The act of inquiry becomes another channel through which the universe records its own behavior. Measurements performed by instruments or minds extend the web of correlations that define the physical record. The reliability of communication between observers depends on shared encoding schemes and mutually accessible records. Language, mathematics, and standardized units function as protocols that align internal representations across different systems. When independent measurements converge, confidence in the underlying regularities increases. Discrepancies prompt refinement of apparatus, method, or theory. The stability of collective knowledge emerges from repeated cross-verification distributed across many participants. Understanding reality as layered description also clarifies why classical intuition remains useful despite its limitations. At scales where decoherence is overwhelming and fluctuations average out, deterministic models provide accurate predictions with far less computational overhead than full quantum calculations. Engineering, navigation, and everyday reasoning operate effectively within this regime. The deeper probabilistic substrate becomes relevant primarily when systems are isolated, extremely small, or subjected to extreme energies. Current research continues to probe the interface between quantum theory, gravity, and information. Experiments with entangled states across increasing distances test the persistence of non-local correlations. Precision measurements of black hole analogues in laboratory systems explore how information might be encoded and released. Advances in quantum computing investigate how coherent superpositions can be maintained and manipulated in controlled environments. Each effort expands the empirical basis for evaluating competing frameworks. The emerging synthesis does not claim that all mysteries have been resolved. Rather, it suggests that the most durable concepts are those grounded in conservation and transformation of information across interacting systems. Matter, energy, space, and time remain indispensable elements of effective description, yet their behavior is constrained by deeper rules governing what distinctions can exist and how they can change. The terrifying aspect, if any, lies not in instability of law but in the realization that familiar appearances are contingent expressions of processes that operate beyond direct perception. Viewed from this perspective, the universe is neither a static collection of objects nor an arbitrary illusion. It is an evolving network in which stable patterns arise, persist for a time, and eventually dissipate as entropy increases. The present moment represents one configuration within that ongoing transformation. The gas on the table, the instruments that probe atoms, and the records stored in memory are all manifestations of information temporarily organized against the broader trend toward equilibrium. As inquiry continues, the most reliable guide remains the accumulation of consistent correlations between theory and observation. Each measurement refines the map without exhausting the territory. The structure uncovered so far indicates that reality is deeply relational, constrained by finite informational capacity and governed by probabilistic rules that yield stable order at large scales. The unsettling insights that emerge from quantum experiments do not dismantle the world. They reveal that its foundation is more subtle than solidity suggests, composed of patterns that endure precisely because the underlying processes obey strict and measurable constraints.